Welcome to NPTEL course on power system protection. We are continuing with transformer protection. In this lecture, we will discuss on inrush issues with differential protection and the detection mechanism, and also we will see how over excitation can be detected. You can say that to overcome the challenges with differential protection. Now, this is a laboratory experiment. While switching on a transformer, small transformer, the corresponding current observed during the no load condition, and the energization leads to current of this nature. So, this is, as we know, is called this inrush current, and this current, if you see, the current pattern is not sinusoidal, it is having a different pattern. This current slowly decays, may takes long time, 20 cycles and so also, and then settles to consider to the normal excitation current, which is 2 to 5% of the rated current. But initially this current, you can say that becomes substantially high, and the associated time constant, you can say that of this current, so called inrush current, is much larger than the time constant, the exponentially decaying DC issue, which we have already understood for the fault situation. The FFT analysis of this current in oscilloscope reveals that it has different harmonic components, including DC and also subharmonic, and so some of the, you can say that harmonic components, second, fourth and fifth is pretty high as compared to the fundamental, and that we see from this table. Now, we will see why this, you can say that large current happens to be there during the transformer energization, and we will try to analyze quickly on a transformer case. So, this is a source with its own impedance and the corresponding voltage, Thevenin's voltage and Thevenin's impedance, we can consider that way. This part you can say is the transformer. So, we have taken the equivalent model, primary side resistance, leakage inductance and the magnetizing inductance path. For simplicity, we have neglected here the core loss part. Secondary part also this associated resistance and leakage inductance, and then the load impedance part. So, this transformer is to be switched on. So, some of the basic equation we know that the corresponding inductance, you can say, is n square upon the reluctance, and reluctance is related to in terms of these parameters L upon, you can say that A mu naught mu r, and the mu naught mu r, you can say, related to B upon H, flux density upon the H, you can say that the H relates to, you can say that this the corresponding magnetizing current aspect, and B relates to this flux aspect. So, this H magnetic field intensity and B magnetic flux density, they are related. So, we know, you can say that the BH curve for the particular magnetic core of the transformer. Furthermore, the flux which is produced by this associated I phi through this, you can say that shunt path is related to, you can say that the voltage in terms of 1 upon n integration of V dt, or we say V equals to d psi by dt, and that relates to your transformer EMF equation also. Now, if you see this graphical plot, which you can find in books more details also. So, this is a sinusoidal voltage, and let us assume that the transformer core, while the transformer was switched off earlier, now we are energizing, having a residual flux of this amount, phi r amount. Now, this voltage we know we can say that will be integrated to provide the corresponding flux for the core. So, this cycle gives us, you can say, this half portion of this because of the integration. So, till this point the corresponding flux goes on increasing starting from this residual flux phi r. Now, this is our, you can say that B H kind of thing. So, B corresponds to flux and H corresponds to the magnetizing current I phi. So, this you can say that part, assume this you can say that part of that B H curve in this positive half. So, then leads you can say that each you can say that point of this voltage we can relate you can say that to the corresponding flux linkage, and from the flux linkage we can correlate to this corresponding current associated with the shunt branch, the magnetizing current. So, what we see that because of you can say that the shifting of this you can say that curve because of the residual flux, it goes to the saturation region of the so called BH curve or the flux versus this I phi, and that results in you can say that the corresponding I phi current to be of this shape and a substantially high current because of the you can say that it is going you can say that in the saturation region. So, to increase a small amount of flux in this saturation region, the associated current requirement in the shunt branch, that is the magnetizing current, is substantially high. So, this you can say that graphical plot reveals that the wave shape of you can say that the corresponding magnetizing current is different, and also the amount of current you can say that in the shunt branch becomes substantially high, and that you can say that that the corresponding during that time, because this mu naught mu r, the mu r part changes substantially from this relation. So, therefore, you can say that the inductance L phi becomes substantially low in the equivalent circuit diagram, and the magnetizing current becomes very high. This current you can say that can be as high as 5 to 7 times of the transformer rated current, and once because this current flows in the one winding only where we are energizing. So, therefore, you can say that the difference current becomes substantially high, and it may lead to you can say that unnecessary unwanted tripping of the relay due to the operation through differential relay. This inrush current what we say has different issues and all associated with the issue associated with the unnecessary tripping. This you can say that current is not only due to transformer energization, it occurs you can say that also when there is voltage recovery after the clearance of an external fault. The energization of a transformer in parallel with a transformer, that we know that sympathetic inrush also, when two transformers are in parallel, this is being observed, and the corresponding inrush current that depends upon numerous factors. Some of them they are the residual flux in the core, the point on the wave, that at what point of the corresponding voltage the corresponding transformer is again switched on or energized, the magnitude of source impedance, because this current flows from the source to the impedance of the source to the transformer, the parameters of the transformer including the core aspect and all these things, which you can see that governs the L phi part and the part of the transformer primary winding parameters, and so as we have observed in the equivalent circuit diagram in the earlier slide. This inrush current generally contains DC offset, different odd harmonic components including even harmonics also, and typically it is composed of unipolar or bipolar pulses like this you can see that we are talking about here. It may be only you can say that in the positive half or negative half, or maybe having some you can say that DC offset also, and separated by intervals or very low currents. So, it is separated by intervals with the having very low currents. These are the set of features. This you can say that special wave of you can say that the corresponding current in transformer happens to be there, and this you can say that plays a nuisance in the operation of the transformer differential relay. Now, during transformer energization, Let us you can say that the example which we have taken in earlier lecture also 33 kV delta side, star side 220 kV, and this is you can say that the source side and this is load side. So, the load is switched off, no load condition, and the transformer you can say that energized, and then you can say that we like to take the different currents through the cities, and then you can say that we process you can say that for the differential relay operations. So, during that one instant of time you can say that it is being recorded that the corresponding you can say that currents in the delta side and the corresponding high voltage side not loaded. So, no currents. So, this side is energized. So, the different phases have different currents at different you can say that positions. So, that is you can say that the corresponding recorded currents we have mentioned here. So, therefore, what happens that the corresponding I operating current after the vector group adaptation and perspective and so. So, the differential current in this perspective you can say that becomes these values. So, these values you can say that if you see the corresponding percentage biased characteristic which we have already enumerated in earlier lecture, the restraining current in phase A becomes 0.44, M1 consider let us say 0.2 and M2 equals to 0.5, and IP you can say that this pickup current you can say that it becomes 0.2 what we have considered earlier also. So, this I operating current you can say that is close to 0.9. So, that you can say that leads to you can say that that it is greater than this also, and also is greater than you can say that our M1 0.2 into 0.44. So, that is 0.09. So, therefore, we can say that this you can say that point will fall in this region, trip region, and then you can say that the differential will trip for the transformer energization case. This is not a fault case. After some time the corresponding current will die down and the differential current will also vanish, and it will be only that spill current you can say that it will be very small 2 to 5% of the you can say the rated current due to you can say to the magnetizing current which will be there. So, this is not an internal fault case, the differential relay should not operate at this time, but if you can say that allow this current and it falls in the trip region. So, the transformer you can say that will operate unnecessarily. So, this is a compromise in the security perspective of the differential relay, and therefore, you can say that some mechanism must be there to avoid unwanted tripping due to transformer organization or inrush situation. Now, I will analyze the corresponding the nature of you can say that this inrush current, and then you can say that we will see how we can say that a proper way of mechanism can be developed for restraining or blocking the corresponding relay during such an operation. So, the harmonic components in the different you can say that the differential current during inrush current happens to be PC. This you can say that what you see for that earlier case energization, it reveals you can say the different harmonic components including fundamental. So, this is fundamental, it goes down, and as already mentioned you can say that it is a large time constant, and you can say that it decays and finally settles to the magnetizing current aspect. It contains you can say that this curve you can say that contains very large amount of second harmonic, that is a speciality, and that we already mentioned also, and it contains you can say that other harmonic components as you see you can say that from third, fourth, fifth, and so you can say that different other harmonic components also. But the issue you can say that in the differential relay is that no third, or you can say that multiple of third harmonic components can be used for you can say that to use for you can say that the block or restrain the differential relay for inrush current, because in the process you can say that these you can say that triple harmonics are equivalent to the zero sequence symmetry, and therefore, you can say that they will be because we have in the process of you can say that differential current we have subtracting the zero sequence component. So, therefore, they will be also eliminated in the process. So, that these you can say that third or its multiple you can say that harmonic components cannot be used for the distinction of inrush situation in the differential relay application. The second harmonic which is a symmetry to can say that to the negative you can say that sequence component, and fourth harmonic which is a symmetry to the positive sequence component can say that can be preserved in the process of computing the differential current, and they can be used you can say that for the purpose of the I am say that inrush current detection perspective, and that is what is being used, you can say that, in most of the relay applications. In the harmonic blocking, you can say there are schemes for inrush situations. There are two schemes, you can say that, one is blocking scheme and the other is a harmonic restraint scheme. We will, you can say that, learn, you can say that, what are these, you can say that, two also in our subsequent discussion. In the blocking scheme, you can say that, typically you can say that when the second harmonic components, you can say that, become greater than 15% or so, you can say that, with respect to the fundamental, the corresponding differential relay is being blocked, considering that this is a situation of inrush. That property, you can say that, or that feature, you can say that, we observe from, you can say that, this being observed from, you can say that, numerous inrush situation as compared to the internal fault. Note that the differential relay should operate only for internal fault between the two, you can say that, sides, you can say that, CT for the transformer protection. But this is an inrush situation, not at all, and you can say that, an internal fault. So, it should not operate in that situation. So, to distinguish internal fault and the inrush situation, one of, you can say that, is way is to block the, you can say that, relay operations. If the relay finds the corresponding second harmonic component with respect to fundamental, typically a set value of 15 to 20%. In harmonic restraint scheme, you can say that, what is being done, that we know that a restraint, you can say that, becomes k magnitude of I 1 plus magnitude of I 2 and so. Then in that, you can say that restraint, you can say that, we add the corresponding harmonic components also, and to ensure that, you can say that, the relay does not operate in those situations also, and they have their own advantages, you can say that, in terms of blocking scheme and restraining schemes. Some of the, you can say, the relays employs both also to exploit these advantages also. Now, come to first, you can say that, this harmonic blocking scheme, you can say that, perspective. So, this is what our conventional, you can say that, percentage bias differential relay. To trip the, you can say that, the corresponding fulfillment requirement, differential will operate, it means that it confirms an internal fault when these, you can say that, conditions are being satisfied. This we have already known, you can say that, the I operating current, that is the differential current in the part, in that part, in that algorithms which we have seen earlier, you can say that, in earlier lectures also, should be greater than this, the corresponding minimum pickup current. I operating should be greater than, you can say that, this M1 or M2, you can say that, the restraining current part, that is in this portion. I operating current should be considered greater than K2 I2, that is the second harmonic component, and this I operating current should be greater than K4 I4, the fourth harmonic component. So, these two, you can say that, two components I2 and I4 corresponds to the second and fourth harmonic components are used for blocking the corresponding relay from operations. How this K2 and K4 are decided, you can say that, the K2 is 100 upon, you can say that, PCT2 and K4 is 100 upon PCT4. This PCT is, you can say that, the percentage setting, you can say that, of the harmonic component, and these, you can say that, are typically set, you can say that, in terms of, you can say that, PCT2 20% and so, and PCT4 you can say that 10% or so. So, that you can say that is about the usage of, you can say that, in these schemes. So, what we see this scheme, you can say that, you can understand from this now, that we know conventional and differential relay, the I operating, you can say that, operates, you can say that, when it is greater than IPU, and the I operator operates, you can say that, when it is greater than, you can say that, M I residual, you can say that, the restraining current perspective, and when these, you can say, satisfied, it goes for a trip decision. So, that we can say that we have learned earlier. Now, what it will introduce, you can say that, the corresponding second harmonic component and the fourth harmonic component multiplied by this corresponding K2 and K4, what we have defined here, and then you can say that, there also you can say that, comparator either of any one, you can say that, can be greater than, you can say that, the threshold value. Then for each phase, you can say that, we will make that, you can say that, things, and then you can say that, we make a blocks, you can say that, operation for this one. So, then you can say that, the overall, you can say that, trip decision can be obtained. So, this is from the normal, you can say that, differential relay perspective, and this portion, you can say that, is from the, you can say that, second harmonic and fourth harmonic perspective, which ensures, you can say that, an inrush synergy situation. However, you can say that, if this percentage, you can say that, becomes much smaller, then this is not at all inrush and this is an internal fault, and in that case, you can say that, the relay will go for a trip decision. Now, let us we can say that see that earlier example which we had, you can say that an aggregation we can say that which we have seen in our earlier slide. So, in that case you can say that we consider now you can say that a percentage of second harmonic setting of 20% and percent of fourth harmonic we can say that of 10% in this case. So, K2 becomes equals to 5 and K4 becomes equals to 10. And now you can say that in our earlier calculations also we have seen, so the corresponding I operating current you can say that is 0.8 above, and then I restraining equals to 0.44 ampere, I 2 equals to negative, I am saying the corresponding second harmonic component at a given instant time is 0.3 ampere, and the I restraining A you can say that in phase A you can say that each happens to be can say that 0.02 ampere. So, now for this you can say that M1 M2 considers to be 0.2 and 0.5, and in that case you can say that we go for IP equals to 0.2 ampere or so. And we observe that you can say that the I operating is greater than IPU, true, that is you can say that 0.87 is greater than 0.2. I operating you can say that is in terms of this M1 into 0.44. So, that gives you can say that also 0.09. The I operating K4 into I4, that becomes equals to 10, the K4 is 10 into you can say that 0.02 is 0.2 ampere, and I operating you can say that is it is observed that it is less than K2 I2, that is the second harmonic components. K2 is you can say that 5 and I2 you can say that we got you can say that to be 0.3 ampere. So, therefore, you can say that this becomes equals to 1.5 ampere. So, this implies that you can say that this you can say second harmonic component is being is not being satisfied you can say that for this operation of the differential relay. So, therefore, the differential relay will be blocked in this case. In overall, we see that with this kind of setting and all these things, for these situations the second harmonic component is not being satisfied in this case, and therefore, you can say that the output becomes a block signal for this case, which is correct, and therefore, you can say that the relay will not maloperate with the help of such a scheme. Now, we will go to the harmonic restraint scheme, you can say that scheme, the second option you can say that which is being used. So, here also you can say that the second and fourth harmonics are you can say that being applied, and in this case you can say that what is being done, as already mentioned, you can say that in the I with the I restraining you can say that we add this you can say that this I 2 K 2 and I 4 K 4, K 2 and K 4 are already defined in terms of the other way also, and then you can say that the corresponding I P you can say that and I P O. So, this is the differential part you can say that which makes the enable you can say that to this comparator also, and in this comparator you can say that we add the corresponding restraining part like this, that the M I R A S plus K 2 I 2 plus K 4 I 4. So, finally, you can say that we are increasing the part of you can say that enhancing the part of the restraining part. So, that you can say that the relay does not malfunction during the inrush situation where the current differential current still is being substantially high. So, this is another way of you can say that doing the corresponding to avoid the maloperation of the differential relay, we call it harmonic restraint option. So, the corresponding harmonics are being so that added to the restraint current for this perspective. Now, take you can say that another example, let us say you can say that internal fault happens to be there in the transformer, and the corresponding you can say that it is not loaded and we energize this. If this is the situation, this relay you can say that should you clearly know that this is an internal fault. So, the relay must trip, even though it may find some inrush behavior and so and so. So, that must be ensured you can say that with this you can say that whatever restraint and so we are observing. Now, in this case you can say that because this is there is no current you can say that in the load side. So, these currents all currents are 0 in case of you can say that high voltage side, but the currents you can say that in this side you can say that low voltage side becomes, these are the set of currents you can say that IA and IB are considered pretty high, that we have already noticed in our earlier lecture also, because this phase is in a phase you can say that is involved in this case. So, now the purpose is to test the differential relay performance with harmonic restraint, how does it function. So, after the zero sequence eliminations we got the you can say that the corresponding differential current you can say that in phase A, phase B, phase C to be this set of current 6.84, 3.69 and 3.21. Consider for phase A the 6.84 the magnitude of current. So, we see you can say that IPU you can say that 0.2 only. So, it means that I operating is greater than IPU, you can say that we know. Now, this I operating now with the you can say that with the approach of you can say that making the restraint you can say that features adding the restraint features to this K 2 and the K 2 I 2 plus K 4 I 4. So, we will calculate the corresponding this part you can say that. So, this part becomes equals to you can say that if you substitute all the values of you can say that this with 20% K 2 and you can say that for the and 10% of for the corresponding K 4, then this becomes 1.734 ampere. So, then we say consider substituting the value, we say that the IPU I operating is 6.84, which is much higher than the 1.73 ampere, and that leads to the situation you can say that the corresponding I operating A satisfied greater than IPU and also is greater than you can say that the corresponding restraint you can say that currents 1.734. So, therefore, the differential will operate you can say that for this internal fault case, which is will be a correct decision. It means that you can say that differential relay including you consider the harmonic restraints, which you can say that is successful you can say that for its operation during an internal fault. This inrush has various other issues you can say that we see here, that whenever inrush happens to be there, all you can say that the phases they are being switched on, you can say that this is a 3 phase situation. So, all are can say that through the different poles you can say that in a circuit breaker they will be switched on, and it is being observed that you can say that all the phases do not see large current due to this inrush situation. So, typically this is you can say that a situation like this, phase A current is in the positive you can say that perspective, and the negative you can say that half you see the phase B, and phase C being very low current you can say that a magnetizing normal kind of current. So, all phases do not see consider large amount of current due to inrush in general. So, in that situation how do we consider that on the phase to phase basis, as we have already enumerated for the percentage biased differential relay to restrain the during the inrush situations, how do we handle that one? There are different solutions you can say that called you can say that cross phase blocking techniques for this inrush you can say that situation. Now, the blocking options we have already learned, but how that is being accomplished in the 3 phase environment, that we like to figure out here. The cross phase word is similar to you can say that the cross polarization you can say that we learn in the differential relay perspective, that in the directional relay perspective. In the directional relay, if you remember you can say that any phase you can say that involved with fault in general. So, that phase voltage may substantially go down. So, therefore, instead of using that phase voltage you use you can say that the other phases voltage for better operation. Here also like that it happens to be like that whenever you can say that in any of the phase you can say that the corresponding inrush phenomena is not observed, but it is observed you can say that in other phases the whole you can say that all you can say that three phases you can say that differential relate decisions are being blocked. So, we see you can say that typically one of the you can say that phases you can say that in the differential element like C you can say that low amount of second harmonic or fourth harmonic component, and that may lead to unnecessary tripping. So, what is being done you can say that there are different options you can say that on these blocking options due to you can say that during inrush situation. Per phase basis, in per phase mode the relay performs inrush resistance individual phase and then block accordingly. But what will happen here in this case, that one of the considered phases will not be having considered resistance. So, the relay may maloperate in that situation also. 2 out of 3 in 2 out of 3 mode you can say that the relay checks you can say that second harmonic levels you can say that in all the 3 you can say that phases, and we finds that 2 out of the you can say that 3 phases they have significant second harmonic greater than the you can say that the restraint like 15% or 20% setting, then the relay will consider that block all the 3 phases. 1 out of 3 in this case, if any of the 3 phases the relay you can say that finds that the second harmonic component is significant, it blocks the you can say that all the 3 phases differential relay operation. There is another scheme available also you can say that it is called averaging schemes. What is being done you can say that the averaging second harmonic average second harmonic component of all 3 phases are being obtained, and that decides you can say that whether the relay is to be blocked or to not to block. The alternative method also you can say that to the this inrush detection process besides this harmonic based approach, and so one is called wave shape you can say that identification approach. Let us you can say that see for this case. So, transformer energizations and internal fault. So, these were the internal fault case and these normal transform energization. So, with the transform energization we have the inrush shape like this or to the negative or maybe very small amount. So, this is the corresponding differential current. When an internal fault happens to be there, the current patterns you can say that with a decaying DC and so may be very close to sinusoidal with some certain DC offset and so. So, what is being done here you can say that if you see this put the dotted lines both in the positive you can say that and negative we put a threshold and the hatched portion is nothing but the area under the curves, above that you can say that the corresponding line in the positive half also in the negative half. So, this we see you can say that we designate that as A positive and A negative and then you can say that they are you can say that the wave shape, the wave you can say that shape is indicative of you can say that whether it is you can say that inrush or the corresponding normal you can say that internal fault case which is very close to the sinusoidal perspective. We will see that. So, what is being considered done a ratio you can say that called a DC ratio. So, that DC ratio you can say is a minimum of you can say that A positive and A negative to the maximum of you can say that the corresponding A positive A negative. What we mean by A positive A negative is the area under the consider this curve above this threshold in the positive half and also you can say a negative half. A negative you can say that if you see here this corresponds to you can say that area under the curve you can say that below this you can say that the threshold line dotted line. So, that becomes A negative and above this you can say that it becomes A positive. So, in the inrush also if something you can say that maybe they are you can say that in case of A negative also sometimes you can say that it goes to the negative perspective also and sometimes it becomes positive. So, or it may be considered both positive and negative also. So, what you find you can say that the DC ratio is that the minimum value upon maximum value of this you can say that positive area versus the negative area. So, what is being observed that you can say that the DCR becomes equals to 0 for inrush condition, the minimum becomes you can say that becomes 0 either you can say it is in positive or it is negative from the corresponding threshold value. And you can say that in case of internal fault the corresponding area because it is very close to sinusoidal. So, therefore, you can say that after filtering out the decaying DC and so then it becomes you can say that for internal fault the positive you can say that value A positive and the A negative becomes they are very close to 1 and that becomes 1. So, therefore, you can say that the DCR value you can say that reveals whether in an inrush situation or you can say that an internal fault situation it can discriminate effectively and the concept behind is that the wave shape approach. Wave shapes for the inrush is completely different than the corresponding sinusoidal nature of the internal fault. So, this you can say that say that for the internal differential current for the internal fault case DCR equals to 0 and this you can this for the inrush situation and for an internal fault you can say that case what we have already narrated earlier this corresponding you can say that curve becomes like this and the DCR comes out to be 0.54 close to you can say that one kind of thing. So, much higher than the corresponding 0 value. So, what we say that the differential current processing and all this thing A positive A negative minimum upon maximum the DCR value we got you can say that and then a 0.1 threshold is being done and then you can say that the corresponding DCR ratio blocking scheme is there to for this perspective. So, DCR here is 0.54 much higher than the 0.1 and therefore, this will for the internal fault case and the DCR value is 0 you can say that. So, this will be for this internal fault case. These are the two examples for wave shape based approach for inrush detection. There is another you can say scheme. So, pretty you can say that old method in numerical concept and so inrush detection by wave form analysis also. So, we know you can say that the corresponding nature of you can say that the corresponding wave is like this and already mentioned from the beginning that it passes through you can say that some of the patches where the corresponding current is substantially small. Now, if you take the derivative you can say that of this you can say that differential current then the derivative you can say becomes here and that becomes you can say that the derivative you can say that also becomes substantially low. So, a logic you can say that either derivative or so different principles are being available in different numerical relays. So, this you can say magnitude of this differential you can say that current differential current the derivative of the differential current becomes smaller than the thresholds. Then we know that at some patches you can say that then you know that you can say that this inrush you can say that can be detected from that where also. So, therefore, you can say that and this you can say is a period some period of time in the system you can say that this goes through, you can say that small value, and that you can say that can be detected by this principle of operation. So, it is being observed that the principle which we talk about in terms of the second harmonic restraint or blocking semi and all these things, they lead to, you can say that delayed process, you can say that in the decision making for the even for the internal fault case and all these things. But that you can say that this wave the wave nature, you can say that which we talk about from this waveform analysis by this approach gives a speedier operation. So, many you can say that reader also combine these two, you can say that perspective to exploit the advantage of, you can say that speed in operation, and that you can say that some you can say that release call it as also adaptive form of protection also. There is another issue, you can say that in the which leads to, you can say that a maloperation of the differential relay is the over excitation. Over excitation, you can say that happens to be, you can say that the magnetic flux inside the transformer key is directly proportional to the voltage, and the voltage becomes higher, then sometimes you can say that it may be higher voltage. The higher voltage leads to, you can say that the corresponding flux requirement becomes more, and to having the large amount of flux, you can say that the associated magnetizing current becomes much more, and in that time also the current becomes substantially higher. So, that you can say that current becomes, you can say that flows, you can say in one side only where the corresponding magnetizing current happens to be there, and that leads to, you can say that the differential current, you can say that to be, you can say that to be significant, and may lead to, you can say that malfunction of the differential relay. Now, this excitation current consists of mainly odd harmonics and so, but as already known, you can say that in the filtering process for the differential current odd harmonics are symmetric to, you can say that to the 0 sequence. So, therefore, they will not be available in the differential current. So, therefore, it is found that you can say that fifth harmonic component is a suitable choice for detection of the over excitation condition in general. Typical setting value, you can say that is a 30% of the fundamental of the, you can say that for this perspective, and one you can say that other option, you can say some the relay use, you can say that the whenever they detect the corresponding fifth harmonic component, they take the corresponding the pickup setting to be raised to, you can say higher value like this, you can say that to as high as 0.6 p, you can say that to avoid, you can say that unnecessary tripping by over excitation situation and so. So, for example, you can say that in this you can say that the 33:220 kV systems we applied, you can say that 45 kV, you can say that to these 33 kV side systems, and the corresponding signal, you can say the nature becomes this, which is having highly, you can say third harmonic component, also fifth harmonic component, but as already mentioned, you can say that the third harmonic component will be eliminated by the 0 sequence component eliminations. So, the differential current will be available, you can say that only significant amount of fifth harmonic component. And then you can say that when you analyze, you can say that the corresponding current magnitudes of different, you can say that harmonic components, and in terms of the percentage of the fundamental also, then you say that you can say that the corresponding the fifth harmonic component, the green one, you can say that is of very high value, you can say that, and which will, you can say that make the corresponding the blocking arrangement for the differential operations. One thing you can say that we say, you can say that that the over excitation resistance for differential relay, the over excitation occurs, you can say that when the volt per hertz also, you can say that of the rated value. This may occur from, you can say that load rejection, malfunctioning of voltage and reactive power support, the voltage high situation, there is a increment of flux in the core that leads to, you can say that the large amount of current in the magnetizing path. And then you can say that the malfunctioning of AVR and all the issues you can say that may lead to such situation, and so the voltage at nominal frequency causes the V by hertz, you can say that to rise, and this causes the transformer core to saturate, and which contains, you can say that large amount of fifth harmonic and so, and that you can say that lead to the differential lead to malfunction in terms of that. So, now to distinguish, you can say that over voltage versus over excitation protection, and note I am saying that you need not confuse, you can say that about this perspective. This is a differential relay protections we are talking about. Differential relay protection should operate only when, you can say that an internal fault happens to be the transformer, and for that you can say that case neither, you can say that the Inrush situation or the corresponding over excitation situation, so allow the, you can say that the differential relay to operate. Over voltage, you can say that leads to stress in the dielectrics, and you can say that also you can say that leads to thermal heating and so, and that is a slow process, is not that fast, you can say that we are talking about in terms of that. Overexcitation also leads to, you can say that, overfluxing, and that also leads to, you can say that, heating of the transformer, and so, and those should be also taken care in terms of their individual. Over voltage protection should be there, overexcitation, you can say that, also protection should be there. Overexcitation leads to overfluxing, and overfluxing can be not only by the fifth harmonic, rather you can say that it will be much better way of capturing by this volt per hertz, you can say that issue, and the volt per hertz Wheatstone curves are there, you can say that, to take care, you can say that, the overfluxing, you can say that, aspect which is be there from the overexcitation issue, and so. So, this is, you can say that, the other, you can say that, schemes available for the transformer protection perspective, but what we are discussing here is on differential relay perspective, which should not function, you can say that, due to inrush or overexcitation situation. So, in, you can say that, overall if we combine all the, you can say that, the harmonic blocking and all these schemes. So, this you can say that the percentage by differential relay that takes the current from the two windings for each phase, and you can say that also that takes, you can say that, here. So, you have, you can say that, the corresponding decision process to be to this one. It takes, you can say that, second harmonic, fourth harmonic, you can say that, the common blocking schemes, also independently you can say that fifth harmonic blocking or operation, and then you can say that operation of this one. There is another, you can say that, schemes which it already talk about in the restraining case, you can say that you can add the second and fourth harmonic, and then you can say that you go for the trip decision, but independently also fifth harmonic blocking will be there, and both you can say that run also parallel, you can say that, and it makes an OR operation to go for this expression. Now, the benefit of, you can say that, this including this kind of, you can say that, integrated scheme is that, you can say that, in case of internal fault and then you are energizing, you can say that, this gives, you can say that, a faster speed decision for the transformer differential protection scheme, and so. So, that you can say that is why some relays you can say that use in, you can say that, in parallel, you can say that both the perspective as already mentioned in earlier also. So, in general we see here inrush create problems, and this current flows in one of the, you can say that, winding. So, therefore, differential relay may malfunction in that situation. To avoid that, you can say that we have different methods, particularly on the harmonic content based approach, and also wave shape, you can say detection approach, and so. And that, however, you can say that it is being observed today that with a newer version of core and all these things, the second harmonic components may not be significant, and so lower and lower. So, that you can say that puts challenges to, you can say that, to the harmonic resistance approach for inrush situations. So, therefore, manufacturers are developing, you can say that, new mechanism to overcome this issue. Overexcitation is another issue, you can say that, when the differential current becomes also significant, and that you can say that is being detected by the fifth harmonic component and from as compared to the fundamental, and that gives a good solution to overcome the issue of unnecessary tripping by differential relay. Thank you.